Hello and welcome back to the Finite Element Analysis series. I'm Bhavik Soneji and today I'm going to talk about derivation of shape function. So let's get started. In the previous videos or in the previous lecture, we were focusing about the steps of FEA. How can we implement the FEA and what are the phases of FEA? What are the steps involved in FEA? So now in this chapter, we are going to focus on one dimension problem. So let's get started. Now, as you are aware about, there are many types of elements available. From those elements, we have to choose one kind of element first. So first, we convert engineering problem into smaller elements. We divide into smaller elements, and we choose any one kind of element first. So in this chapter, we are going to focus on 1D element, that is one dimension elements. So for that, there are different problems like beam, then bar, then truss. All these are example of 1D element because we are only focusing on the change of property in one direction only. So that's why these can be considered as a 1D element. First, we need to understand the difference between these things. What is a beam, what is a bar, and what is a truss. So first, if we consider the bar element, it it can only take the axial load, while the beam can take axial load as well as torsional load. And bending moment also. So if we are only focusing on axial load, then we can take a bar. If we are focusing on torsional force or axial force or any other bending force, then we have to consider beam problem. And truss is the combination of various bars, assembly of bars. So this is the difference between beam, bar, and truss. So now let's understand what is shape function first. So for utilizing the whole screen, I am closing down my video. So first, what is shape function first? So for example, this is my 1D element which is having two nodes, node number 1 and node number 2. So now I can find the field variable. For example, in this example, we are taking field variable as displacement. That is denoted by U. So this is my field variable. So we can find the displacement either on this node or this node. For in between any point, let's say this is point P, in between anywhere it can be. So at point P, we cannot find the value of this field variable. So to find the value at this random point P, we have to interpolate, or we have to develop one function which interpolates, and that interpolation function is nothing but the shape function, so that we can predict value of field variable at any in between point except the nodes. So that is known as shape function. Now we are going to see the relationship between uh, shape function. We will derive what is shape function. So to understand the shape function, first we need to understand there are basically three coordinate system we are going to see in this chapter. First is the local coordinate system. Second is the natural coordinate system. And last is the global coordinate system. So first let me give you example of local coordinate system. So suppose we have a datum plane here and the element is like this. So this is my 1D element which is having two nodes and any random point P. So from datum point, the node number 1 is at x1 distance, random point P is at x distance, and node number 2 is at x2 distance. So if here x, x1 and x2 are the coordinates in x direction, now let's consider a natural coordinate system. So same, again we are taking the same element which is having two nodes 1 and 2, but here we will take the datum from midpoint of this element. So let's say P point is here randomly. Now the datum plane will be different. So here, from here we will have a datum plane. Here datum plane is here, and in natural coordinate system datum plane is here. So at the datum plane we have the value of shape function equal to 0. So in one direction the value of shape function is negative. So here at node number 1 it is -1, and at node number 2 it is +1. So by taking the reference from midpoint we can calculate, and the psi value For p point it is psi value. And for global coordinate system, we are considering the assembly of whole assembly of system. All assembly of all elements. So globally we are taking the global coordinate system. So now let's find out the relationship between the local coordinate system and natural coordinate system. So we can here the common thing is the length is the common thing. Length remains same for both systems. So comparing the length in both direction. So here 1 minus p divided by 1 minus 2 for local coordinates is equal to 1 minus p divided by 1 minus 2 for natural coordinate system. So the length will remain same. So now we can see if we put the value like this, it will be x minus x1 upon x2 minus x1 equal to 1 plus I by 2. So if we want to find the value of natural shape function, it will be 2 into x minus x1 divided by x2 minus x1 minus 1. So this is the relationship between local coordinate system and natural coordinate system. And natural coordinate system. So you have to remember this equation. You can note it down. At any point you find it difficult, you can check the previous videos where we have implemented this, and we will take this calculation for our further explanation. So now let's understand what is shape function. So in the first step we have derived the relation between the local and natural coordinate system. Now understand how the shape function, what is shape function. So this is my element. So we have two nodes, node number 1, node number 2. For example, at node number 1, the deflection is first let me say at node number 1 the value is -1 and node number 2 it is +1. In between midpoint it is 0. So this is a two noded 1D element. Now considering the deflection, for example at node number 1 there will be deflection like this. Let's say the value is u1. At this point node number 2 the value is u2. So in between any point, at any point if I want to find, I have to assume that one function which satisfy the linearity. So first we assume that the within element function is linear. Now let's uh, denote it by, we can have two shape functions. So first shape function is n1, let's say, and second possibility the shape function will be n2. So here the a point represent the node number 1, b point represent node number 2. In this case e and f uh, represent node number 1 and 2. So for example randomly we are taking point p. So p has a slope value like this. Let's say it is a d point, here it is a h point. So first we have to find the slope. So slope will be the same for both the cases. Slope will be the same, will become the same. So taking the slope here, p point. So in by combining both things we can write pd divided by ac equal to pb divided by ab. Same for this thing, it is ph divided by ef and pf divided by ef. So here the value is unity, that is 1. Same for this thing, this triangle has value unity 1 here. So if I want to define n1, n1 will become 1 minus e psi divided by 2, and here n2 shape function is defined as plus because the value is plus. Now total u is a combination of u1 into n1 plus u2 into n2. Here capital N1 and N2 are the shape function and u1 and u2 are the displacement. So we can write this thing in a matrix form like this: n1, n2, and in vector u1 and u2. So this element is a element shape vector, and this is the nodal displacement vector. So if I want to write this in terms of x will be equal to n1 x1 plus n2 x2. So this is my shape function. So this is how you can derive the shape function. At any step, if you are finding it difficult, you can pause and see it again. Hope you understood it. So in the next lecture, we are going to derive the stiffness metric for the same 1D element.